Welcome. I'm going to talk about problem drift in control. And so problem drift is this phenomenon where when people are working on a problem together, as they slowly solve the problem, they kind of look past the horizon of the problem to bigger and better things. And now they try to solve those bigger and better things. And then maybe they don't realize when they have actually solved the original problem because they're so focused on what they're currently working on. And so I'm going to talk about how this interacts with value iteration in the control problem in reinforcement learning. So I'll first start by talking about value iteration for a little bit, and then we'll go on to a discussion. So value iteration is an algorithm that's from 1957, and it's designed to find the optimal policy for a Markov decision process. And so I'll explain what that means. A Markov decision process is composed of a list of states S, some list of actions A, and then a probability of transitioning from one state to another when you take an action A in that state. You also get some reward, average reward, associated with taking an action in a state. And there's this discount factor gamma that is basically telling the agent how much it should care about rewards that are in the future versus rewards that it gets right now. And so an optimal policy is a list of instructions for each state of which action that you should take. And if you follow this optimal policy, you're going to get the maximal reward possible according to how much you care about the future rewards and how much you care about current rewards based on gamma. So with value iteration, you start with some arbitrary value function Q0. And so Q0 I wrote with S and A because it's the value of taking a state, an action A in state S. And value iteration works by applying this operator T to your value function many, many times. And I just wrote T like this because it depends on the probabilities and the rewards and the discount factor. So if you don't know the probabilities or the rewards, you will not be able to use this T. And it doesn't really matter how it works, but if you apply T to a value function, you're going to get another value function, and the values that are stored in that function are going to be at least as high as the values were previously. And so if you apply this operator many times, eventually you're going to converge to Q star, which is the optimal value function. So that means if you apply T again, the values in the value function are going to remain the same for every state in action. And now you can use this optimal value function to find an optimal policy. And this is the thing that we wanted to find in the beginning so that we can execute some agent in this MDP and acquire the maximum amount of reward. Right, so sometimes this can be a bit slow because you have to look at every single state in action every time you apply this operator. And so in 1982, Bert made this asynchronous version of value iteration where instead of applying the T operator to the whole value function every iteration, you can just apply it to a single state action pair in that value function. And so depending on the order that you do your updates, you might be able to converge faster than if you were just doing the update to every single state action pair in a loop. So the really cool thing about this algorithm is that it doesn't matter what order you do the updates to the state action pairs, as long as you update every state action pair infinitely many times. And then at the end, you're going to end up with convergence to Q star, and you can find pi star in exactly the same way as you did before. And this is the last setting that I'm going to talk about where you know the transition probabilities and the average rewards. And the next setting where we're using Q-learning is much more like this reinforcement learning setting that we see when we first learn about reinforcement learning. So we have the same states and actions, but now we don't know what the transition probabilities are, and we don't know what the average rewards are. So to figure these out, we are going to have to interact with the environment. simulate some state, simulate taking an action, and then encounter some new next state. And with Q-learning is really cool. It has a lot of the same guarantees as you would have in asynchronous value iteration, as long as you are visiting each state action pair infinitely many times. So that means you visit each state infinitely many times, and then when you're in that state, you have some non-zero probability of taking each action. As long as you run this for long enough, you will converge to Q star. And then you will be able to actually get the optimal policy out of this. And so this was a really big deal in 1989, because this was kind of the big reveal that it is possible to find Q star even if you don't know the transition probabilities and the average rewards. But of course, this isn't enough, because sometimes you have way more states than you can ever possibly hold in memory, or you have some continuous state space, and so it doesn't really make sense to represent a value function with, if you have a continuum of states, you can't have a single value associated with each state. So we have linear Q-learning, which was not, I couldn't find the original paper for linear Q-learning, but I think it was shown in 1993 that linear Q-learning does not necessarily converge, or does not necessarily find the optimal policy. So sometime between 89 and 93, we have linear Q-learning being analyzed somewhat. So linear Q-learning differs, like I said, because there's a finite list of states S. We don't have the finite list of states S. Instead, we have some observation space O. And we have now a linear function representation. So that means we, at every time step, instead of seeing a state, we see some observation vector. And we're going to store some weights that we multiply with that observation vector to approximate the Q values. And now, because of this approximation, we will no longer converge to Q star. And we can no longer find the optimal policy from this Q value that we're learning. So the first problem, where we're not going to converge to Q star, is partially due to this deadly triad that Rich talks about in the textbook. So Q-learning uses function approximation and bootstrapping, and those are kind of two integral parts of the algorithm, so you can't really get rid of those. But like I said before, the exploration through the environment is kind of arbitrary. As long as you visit all the state action pairs infinitely many times, you can do whatever you want. And so if you do off-policy exploration with function approximation Q-learning, you're going to have a really hard time learning the actual Q values. So the solution to this is to follow on policy, a policy that is specified by the Q values that you're currently estimating. So in the same way that when you find Q star, you can convert it into a policy. You can look at whatever approximate value function you have at the current time and input your observation vector and see which of the action values has the highest estimate, and then you would take that action as you go through the environment. So if you do that, you will be able to learn some action values, but you will not be able to visit all the state action pairs infinitely many times. So there's this tension between these exploration and actually learning the value function that is causing problems here. And then the other problem is that since your value function is approximate, when you try to turn it into a policy, even if the approximation is pretty close to the true values, the policy might not be pretty close to the optimal policy, in the sense that the reward you get by running the approximated policy might be very different from the reward you get if you run the optimal policy. So now with the linear value function approximation Q-learning, you kind of just have to hope that it works. and you don't really have any guarantees that say it's going to do so. So one of the big problems that makes linear function approximation Q-learning difficult to apply in practice is because the approximation of your value function might not be so good. So one of the solutions to that is to use a better function approximator. And so if you have a nonlinear function approximation like dqn, you can actually approximate the value function more precisely. And then you would hope that the policy that comes out of that better approximation of the value function is closer in terms of reward to the optimal policy rather than the linear approximation policy that you had before. So as we've gone through these past slides, you've seen like the MDP side of the slides has changed quite a bit. We no longer know the transition probabilities, average rewards, and the state space has turned into observation space. And it's now the right-hand side with the algorithms has gone from having very nice guarantees to kind of hoping that things work. And so what do we have to do to make, what has to go right if we apply dqn so that it actually finds the optimal policy? So I mentioned this a little bit before, but we have to select actions so that we can balance between exploring, which means we visit each state action pair infinitely many times, or gathering on-policy data, which is necessary to allow us to learn the value function. And then also, by chance, the function approximation value function has to be able to learn some value function that's very, very close to the globally optimal one. But since we're using deep learning, this is by gradient descent, and we're guaranteed only to find a local optima. And so even if dqn stops learning, the value function that it finds might not be close to the globally optimal value function. And then, on top of that, the approximation of your value function has to find a policy whose reward is very close to the reward that you would get following the optimal policy. And this is also a big question. It is maybe more likely that this will happen if you use a deep Q-learning rather than linear Q-learning, but it's still not something that's guaranteed. All right, so quick recap. Value iteration was originally introduced for a completely different problem setting than the one that we're applying dqn for. We have known MDP dynamics, so we're just kind of staring at the MDP specification and running our algorithm until we figure out what the best thing to do is, versus we're throwing an agent into an environment and it has to interact and figure out what the best thing to do is by experience. And then in the original setting, we have tabular value functions that were able to express the action value for each state and action, and there is such a thing as like each state and action, whereas now we have some approximation where we might have infinitely many states, or we might not even be able to tell which state we're in because the observation isn't giving us enough information. So the problem is totally different. And this means that while dqn works empirically sometimes, there isn't a guarantee that it's going to work when you move from one problem to another. So given this, what do I want things to look like instead? So I made a little diagram, which I will gradually reveal to you. So a control agent has to take some actions. Like, that's the whole point of the agent. So some actions are going to come out. And what's going to decide which action is coming out is going to be some action selection mechanism. And to make any sort of action selection or decision, it's going to have to be based on information that comes from the environment. Otherwise, it's going to be some purely random action selection. And so this left side represents information coming in from the environment. But I'm using it to mean only like current information. So we have to store some information from the past in order to have enough information to make our action. Like maybe the action right now really depends on something that happened 5 minutes ago, right? You can't just depend on the current time's information. So this is like a super basic diagram. So I just wanted to show you how DQN fits into this diagram and what kind of implications that has for how DQN works. So with DQN, the information is stored in the value function, and the actions are selected using some epsilon greedy or fancier action selection method. But I mean, epsilon greedy is good enough for this talk. So because we're using value iteration as the kind of base of this DQN algorithm, everything is centered around learning the action value function, because in value iteration, everything is centered around learning the action value function. And only at the very end, after you converged, do you get to find the optimal policy. And so similarly in this case, all of your epsilon greedy action selection that you're taking is devoted to making sure that you learn that action value function. And I think this is kind of a wasteful system in that for control, you don't really care what you're learning. You only care that you're picking good actions. So anything that you learn should be so that you can pick the best actions possible in the future. And maybe action value functions are good for that if you have a perfect one. But if you don't have a perfect action value function, I'm not so sure that it's useful or necessary to store all that information to pick the next action. So kind of what I've been trying to say is you have to explore the world according to your action selection mechanism, epsilon greedy. I guess I should explain that. So epsilon greedy is where you usually follow the policy that's specified by your action value function, but with some small probability, you take a random action. And so that means that technically it is possible to visit all state action pairs infinitely many times, but depending on how big epsilon is, it's going to take an incredibly long time to do so. So anyway, back to this. You're exploring the world according to epsilon greedy. And the purpose of this exploration is to learn the action value function. And then at some totally unknown time, you are going to output this policy that is supposed to be close to optimal based on what you've learned from your exploration. And I think that this really doesn't make sense in the context of interactive control problem where you're in the world and you're taking actions and you're seeing what kind of reward you're going to get. So as an example of something that makes more sense to me in this framework, I have policy gradient. So policy gradient is a straightforward algorithm. You have some parameters that specify your policy. So they say basically how likely are you to take some action in some state. And so that's basically all you need to store. And then to take an action, you just sample from that distribution that your policy specifies. And the whole thing is updated using gradient descent on an objective function that specifies that getting more reward is good, essentially. So you're always going to be moving your policy parameters in the direction that will get you more reward in the future. So this is the kind of simple mechanism where I think it's really going to be more useful or more efficient in terms of computation in the control problem, where you have action selection and everything else that you do in the algorithm is devoted to selecting better actions. All right, so to summarize, value iteration is a tool that was developed to solve this non-interactive problem where you have all the information about your MDP and you're just looking at it until you find the optimal policy. And today, we're mostly interested in the problem that involves interacting with the environment and not just like seeing all the information about the environment right in front of you. So at first, we were able to use value iteration to address the interaction problem for more simple versions like the asynchronous or the tabular reinforcement learning versions. But now the problem is much different with function approximation and mostly function approximation, I think. So to be able to converge on a solution in the case that we care about, we're going to have to use something that isn't based on value iteration, or find a really clever way to use value iteration as just like a component in this structure rather than the like key thing that we want to find to be an action value function. I just think learning an action value function to do control is maybe not the best solution. Yeah. So thank you. Yes.
So, can we say much more about convergence with policy gradients than we can with value iteration in the function approximation regime?
So we can't say more about convergence in the sense that they're both using gradient ascent, so they're both going to be finding some local optima. However, because policy iteration, or policy gradient is directly approximating the policy, and value iteration is finding a value function to then approximate the policy, it's a little bit more direct. And so I would expect the solution to possibly be better with policy gradient because of the more direct nature. Although I know the objective function that policy gradient uses can be like really messy, so the local optima might be pretty bad. But just conceptually, I think policy gradient is cleaner, and there should be some way to, I don't know, constrain the objective or something to make it easier to solve.
So what are your feelings about the methods that are in between those two, just like actor-critic methods that are in both the value function and the policy?
So actor-critic is really cool because it learns a value function, but the only purpose of learning the value function is to improve the policy more quickly, or with less variance, I guess. So it has the same properties of policy gradient in terms of the direct nature of all the things you're estimating. And it's just using the value function as like a helper. Whereas with value iteration, the value function is really the center of the algorithm. And yeah, so with that actor-critic, I think the center of the algorithm is not the value function. And I think that's important for a control setting. Martha.
So are you going to explore these, is that possibly your thesis, to explore pushing in these three directions, or no, seriously, it's a question, right? Because you have ideas, but there's not really evidence. It sounds more like a gut feeling that you're telling us rather than based on theoretical or experiential evidence or something. Is that true? Maybe I'm misunderstanding.
So the last thing I talked about, where policy gradient is like more direct than value iteration, that is more of a gut feeling than something that I've explored the like theoretical or empirical nuances of.
But
and
you're gonna, you'll check against actor-critic and policy gradient, whatever else someone may come up, for example, yourself.
I'm interested in thinking about this more. Yeah, this was really fun to make this talk, so I do want to think about these things more. Yeah.
So I think this is a really interesting issue because I guess for me, like policy gradient methods are kind of wrapped up with continuous control reinforcement learning, and for me that's kind of like the wild west of empirical reinforcement learning. It's definitely been the target of a lot of these high-profile studies about reproducibility in machine learning and sensitivity to parameters and sensitivity to random seeds and stuff like that. But I actually don't have a good sense of whether that's due to policy gradient methods or if it's due to just the difficulty of the problems they're operating on, right? Like they're continuous action spaces, so they seem much, much more difficult. You thought at all about that?
Actually, I haven't thought about continuous action spaces much at all. Most of the empirical stuff that I've done has been with discrete action spaces. And even in this talk, I just wanted to use like the concept of a policy gradient method as something that's clean and promising rather than something that I actually think is the way forward, because I just don't know that. Yeah.
I think in one of the slides you mentioned that the applicability of DQN to different domains, it may not be applicable in multiple domains.
Well, okay, so you want me to clarify what I meant by that, right?
Yeah, and do you think that like a policy method would be like universally applicable to any domain? Or yeah, just clarify that statement.
Okay, so the statement about DQN having limited applicability basically came from looking at the results on Atari in the 2015 paper, where sometimes DQN works and sometimes DQN doesn't work, and it's if we're using a control algorithm to do something, we want to know that it's going to work, right? So that's what I mean by limited applicability. Because it doesn't have guarantees, you can't always use it, but sometimes the function approximation and policy all line up so that it's able to perform well. Policy gradient is, so policy gradient or actor critic specifically is, I think, widely useful, but I don't know how big of a problem the gradient descent local optima issue is going to be in practice, just because I have only used actor critic a little bit, and the times that I have used it, it tends to be kind of slow because you have to learn the value function and then update the policy and at different time scales, and that has made it slower in my experience than action value methods. But it does seem promising to me. All right, thank you. Yes.
So, is it true to say that like action value is not stochastic, but then we want to drive a stochastic policy out of this?
Right, so action value methods, if all the action values are different, to make a greedy policy from that action value function, you will have a deterministic policy. But it's possible, so if you have, for example, finite actions, you can make a distribution over the actions based on how high the action values are. So if the action value is higher relative to the other action values in that state, you're more likely to pick that action.
No, I'm trying to say that we don't model the environment stochastic environment, but then we want to drive a stochastic policy. But in policy gradient, from the beginning, we defined it as a stochastic policy, and we want to learn it. So maybe that's the reason why like DQN is limited compared to policy gradient.
Yeah, so DQN, when it's run, usually uses epsilon greedy policy, and I'm not so sure if the actual point of running DQN is to find the policy that it gets at the end. I think even that policy might be run using some epsilon greedy noise in order to make it work. So yeah, your point about policy grading being inherently stochastic and action value methods being not inherently stochastic is true. And it's yeah, so policy gradient is definitely more naturally applicable to stochastic environments. Yeah. Yeah.
It kind of seems like in order to get away from value iteration, we might need some new tools. Like, would you consider model-based RL to be a different, like an approach that might be able to overcome the reliance on value iteration?
So you mean like if we do some planning, then? So I think planning is a method that you can use to update the value function more often or more accurately, or with some specific experience that you want to update it with. But I think you can do that for value iteration or policy iteration or some other method that I don't know about. So I don't really see it as a as different or as inherently separate from the value iteration method. I think you can use it to, yeah, like DynaQ, I guess, uses planning and some aspect of value iteration. So. All right, thank you.